Let me share my screen. Okay. Now one more example, a very quick one. The same concept. So we need to solve a rigid plane flame question. So the first thing you look at the diagram. So we have a two beam here, element 1 and element 2. And the second one, you look at the axis, xy axis and the x prime axis. There's an angle given. So x prime for element 1 is 45. And then x to x prime will be 0. The angle will be 0. Okay, the first, you look at the diagram, look at the element, count element. The second one, look at the axis. The third one, look at the boundary condition. Point 1, mount to the floor. Point 3, mount to the wall. So point 1 and point 3 don't have any movement. So your V1, your U1, V1 rotation 1 will be 0. U3, V3 rotation 3 will be 0. So you can simplify your matrix later on. The next one, you look at external forces. In this case, we have a distributed load. And again, when you look at distributed load, you can always convert them to a focus load by using appendix also. I'll be using appendix in this model, in this module. All right, so we need to find all the displacement, all the value for this system, for all the points. So E value is given, A is given, area is given, I is given. So I here is 1000 for both elements here. So what are the first steps? So first step is to write the 5 matrix that I asked you to write on the question, the 5 marks matrix, write in the answer sheet. Then you get the 5 marks. After that, you look at one by one. The first step is that, all right, you convert the distributed load by using appendix D, like what I show you on the screen here. This one is the well-distributed load, case number 4. So you convert this distributed load into F and M. F1 means on the left here. F2Y is this one here. M2 also here. So you convert this distributed load into all these forces. All these forces. So you have F2y, which is here. F2y will equal to negative WL divided by 2. You copy from here. Although here it show you is F1y, but if you look at the diagram, this the on the left hand side of element 2 is 0.2. So you write F2y equal to negative WL divided by 2. Moment you copy from appendix D. So moment at point 2 will be negative WL squared divided by 2. Same you apply for point number 3. Okay. You substitute all the value. So W given, L is given, and so on. You calculate these two, F2y, M2 from appendix D. You do the same for point 3. Point 3 you copy from appendix D. F3y is this one, negative WL divided by 2. M3 is this one, WL divided by 2. WL squared divided by 2. You substitute the given number, the value, you'll get the value for F3y and M3. So you have, after you have all this value, you convert this diagram into a new free body diagram or a new diagram, as you can see from the screen here. You convert this 1000 Newton meter distributed load into the 4 forces, into force and moment. You can see the arrow is pointing down and the moment also. So you convert distributed load into force and moment. Then you continue with the normal analysis that we covered just now. So this example is to recap how you apply appendix D, or when you look at distributed load, what you should do. You look at appendix D, convert them into focus load and moment, as you can see from this diagram. All right, so I just fill in all the numbers lah. Okay, so all negative value all there. After you convert into this diagram, what do you do? you continue with the calculation. So you look at element 1, again, like what Katana mentioned just now, the question I asked for Katana. What is the summary of the steps? So the first one, find the angle. The angle is 45. Right, from x to x prime, 45. Then you find the cos and sine, and then all the value, right? All the constant value in the very big matrix just now, EL, and so on. This one. All right, we find the EL, 12i divided by L cubed, 6i divided by L, and this one, E divided by L. So you find all this value. After that, you substitute inside this very big matrix. And again, you look at element 1. Be careful that the first 3 column here is referring to 0.1. The last 3 referring to 0.2. So U1, V1, rotation 1, U2, V2, and rotation 2. All this number. Okay, once you get the complete matrix, you know that for 0.1 is mount to the floor, so you can use a ruler to close for U1. U1 not able to move, V1 also not able to move. There's no rotation for 0.1 also. So from the first equation, first matrix here, you only left out the 3 times 3 matrix over here. You only have a value for U2, V2, and rotation 2. This is for element 1. After you're done for element 1, you repeat the same for element 2. So element 2, angle is 0. You calculate the cos and sine. You calculate all the value for the rigid frame stiffness matrix. You calculate the EL. You calculate the 12IL square, 6I divided by L. After that, you substitute the number. And you look at element 2. 0.3 is cannot move. So again, you use your ruler to close the matrix. All right. So L3, the U3, you close. U3 is here. You close the U3 row and column. You close V3 also. You close rotation 3 also. So again, you're only seeing U2, V2, rotation 2 value here. After you get K1 and K2, of course, you can write the whole thing into a big one, but this is a more faster way to solve it. You can write in the 6 times 6 matrix, then you slowly close one by one according to the boundary condition. In this case, I straight away look at element, and then I close the respective row and column, and then I summarize. So I have K1 and K2 for element. I combine them into 1, F equal to KD. These two K1, K2, I combine into a very big K. So I won't go through the process. So as long as you understand the concept, how we solve it. You combine the element 1 and 2, stiffness matrix into a global matrix K. And then you write F equal to KD. All right. So you know that from your matrix, you only have value for U2, V2, and rotation 2, the D here. So you only look at 0.2. So again, U represent X, so F2X. V represent Y, so F2Y because it's referring to 0.2. Rotation 2 means there's a moment there, so moment 2. The K is 3 times 3 matrix that you summarize from the superimpose between the element 1 and element 2 K matrix. Then you solve for three equation here. Again, for this module, I will recommend to go ahead and use simultaneous equation to solve the unknown in the matrix. So here you have 3 equation there. By using simultaneous equation, 3 simultaneous equation, you solve it, you're able to find the answer. All right. So you put all the value. So F2x, if you look at 0.2, there is no value for x, but there is a value for y. After you convert from the appendix D just now, the distributed load really converted to F, 2y, and m. So there's a value for 2y and m2 here. So you substitute the value inside the matrix and you're able to solve, right? You have 0, minus 20,000 minus 30,000 something. You have 3 equations there. So you're able to solve for U2, V2, and rotation 2. So you get the number for displacement U2, V2, rotation 2. After that, you substitute back to a very big. Once you get U2, V2, rotation 2, you can go and solve the other parameter. So again, for this module, you need to understand when you get negative, what does it mean? Positive, what does it mean? And then be careful on the rotation. The unit is radian. Don't write this one as degree. Yeah? So rotation is in radian. So when you look at element, once you find the U2, V2, rotation 2, you look at element 1, this one. You use this equation again, F prime equal to K prime TD to look at element force. F prime equal to K prime TD. So for element 1, you only look at element 1. So again, rewrite the T from the 5 equation, the 5 matrix that I asked you to write in your answer, the 5 marks free marks matrix. So T equal to this one. D is what you find just now. For element 1, you look at point 1 and point 2. U1, 0, V1, 0, rotation 1, 0. U2, V2, rotation 2 is what you find just now. You calculate the T times D. You take this matrix times this matrix. All right. You will get one new matrix with the blue color. Then you continue multiply this answer with the K prime. So recall what is K prime from the 5 marks matrix that I asked you to write in your answer sheet. All right. You're able to find the F prime for element 1. So F prime 1x equal to 1 value. By using this matrix, this equation, F prime equal to K prime TD. So you're able to find the value for these forces. F1x, F1y, M1, F2x, F2y, and M prime. You get the answer for that. And again, be careful on the unit. The moment is Newton meter. Force is Newton, yeah? So be careful on this. Then after you get this one, you need to know, okay. After this, you proceed the same procedure for element 2. So element 2, you can find the same procedure. So you get all the forces for element 2. Then you draw free body diagram. So this is the textbook answer. So you transfer the element 1, the F1, X1Y, M1, F2X, F2Y, M2 into this free body diagram. So you have all this value, you fill in all the value. This is just a guideline for you to draw the free body diagram. You put in the moment, the force in X and Y direction. And again, the X and Y is X prime and Y prime. The X is X prime, Y prime. Same with element 2. So when you draw the free body diagram, remember to put back the distributed load when you draw the free body diagram. Okay. If you do not, if you do not draw this one, you need to put back. You need to draw the appendix D diagram into this one. You can convert this one. You can convert this distributed load component, adding with the additional force and moment. All right. So this is how you do it. How you solve for this kind of question when you have a distributed load. Okay. So this is how we solve for this kind of question. Okay. All right. So let me stop the recording.